So starting with the idea of the oppositely charged parallel plates and this idea of holding an electron against its will by the negative side, we developed the idea of what's happening inside a battery. This reaction produces energy, forcing electrons to the position where they don't want to be, storing a lot of electric potential energy in the system, and then if you provide an escape route, those electrons can leave and go to other parts of a circuit running some sort of electrical equipment, and then come back into the battery and round they go. Just building on this idea, the potential difference across the plates we now call voltage, which is something you've probably heard of before in terms of electricity. So like a D-cell battery is a 1.5 volt battery, that's the voltage of it. And when we draw a battery in pictures, we use a symbol. These long line and a short line, where the long line represents the positive end, that's like the positive plate here, the short line represents the negative end, and these are just wires coming off. So let's see how the oppositely charged parallel plates originally got their charge. Let's draw a source of voltage, a battery, and two uncharged parallel plates. Let's say the battery voltage is 12 volts, that's the potential difference across them, across the terminals, and normally we call the lowest potential 0, but for reasons that will become clear soon, we're going to say that the positive terminal is at a potential of positive 6 volts, and the negative terminal has a potential of negative 6 volts for a potential difference of 12 volts. The plates start off uncharged, so we're going to put equal numbers of protons and electrons on the top plate and equal numbers of protons and electrons on the bottom plate. And just be aware that once things start to happen, the electrons, of course, are going to be moving around. So you may not want to draw them yet. It's up to you how you can manage your picture. Let's say each of the plates starts at a potential of 0 volts because they're uncharged. And that's going to then create a potential difference when we compare it to the battery. Okay, so the plates are uncharged. We want to charge them up, so what do? We run wires from the positive terminal of the battery over to the top plate, and from the negative terminal of the battery over to the negative plate, the bottom plate, excuse me. And what's going to happen now? Well, now the electrons on the plates will sense a potential difference, and they're going to start to move. So let's start to look at the top plate here. Of course, it's always electrons that can move, and electrons start here at a potential of 0, it's like sea level, and over here they see a potential of positive 6 volts, that's like the top of a mountain. In our analogy, of course, electrons, or negative charges, are like helium balloons, and when we release them, they like to go up. Or you could say the positive terminal here has a lot of positive charge. Either way, electrons are going to want to travel through the wire and get to this position. So one by one, electrons will leave the top plate, travel through the conducting wire, and then get to the battery, like the top of a mountain. But once they get inside the battery, well, now the battery does its job, like we were talking about. The chemical reaction produces energy, forcing electrons to the other side, where they don't want to be. So now this electron is at a position of negative 6 volts, and all the way over there is a position of 0 volts. This is down in the valley, this is at sea level, and now the electron wants to go as far away from the negative charge as possible, up the incline here to a 0 volt position, and so the electron is going to run away from the negative terminal and get as far as possible, stopping at the negative plate. Why does it stop there? Well, in between the top plate and the bottom plate is just air. And air, of course, is one of the best insulators around, so electron can't jump the gap, and so electron just stops here. So now, the top plate is getting a little positive, and the bottom plate is getting a little negative. The plates are not at 0 volts anymore. They're starting to develop a potential difference. And one by one, more electrons are pulled off the top plates, because they still see a potential difference that they're still not, at the potential difference that one is, and so it sees a higher potential there. The electron runs to the top of the mountain, the battery does its job, shoving the electron where it doesn't want to be, and now this electron wants to get as far away as possible, so it runs away and ends up on the bottom plate. And so one by one, this keeps happening. Let's say one more charge does it, one more electron does this. It runs there, far away, gets shoved by the battery to the other side, and runs as far away as possible, and there we are. Okay, when does the process stop? Well, we've discussed this idea. We said that charges move until, let's see if you remember, had something to do with the conducting surface. Charges move until the conducting surface is an equipotential. And we did some demonstrations with this in class. So electrons will stop moving when the top plate is at the same potential as the positive terminal, because this is all one big conducting surface. So what is the potential of the top plate now? Well, it's going to be positive 6 volts, because it's connected to a position of positive 6 volts at the positive terminal. What about the potential on the bottom plate? What must its potential be? Well, hopefully you see the bottom plate is connected to this conducting surface to the negative terminal, which is at negative 6 volts. So what's the potential of the bottom plate? Negative 6 volts. At this point, all of this stuff is one big equipotential. All of this stuff is one big equipotential, and neither conducting surface has an electric field anymore. It's like flat line. It's like flat ground. There's no more reason for electrons to move in either one of these because those surfaces are equipotentials. And now the process stops. And now there's a potential difference between the plates of how much? 12 volts, which just happens to match the potential difference across the battery. Great. So the top plate lost 3 electrons. Now, of course, in reality, it loses many, many more, right? These are just representative of the billions and billions of electrons, but let's say, for example, it lost 3 electrons, and the bottom plate gained those 3 electrons. And so now we have equal and opposite charges. Whatever charge the top plate lost, the bottom plate gains, and we've created the oppositely charged parallel plates. That's it. That's how it's done. But what can we do with these oppositely charged parallel plates? Well, we can actually use it as what's called a capacitor. There's now energy stored in this arrangement. These electrons don't really want to be there, right? They're forced there by the battery, hanging out by other electrons, and the top plates lost electrons. These electrons really want to be at the top plate, so there's energy stored in this system, where we say it's stored in the electric field between the plates, and now we call this a capacitor. So what we can do is we can disconnect this whole system from the battery, and the plates will retain their charges, they'll retain their potential difference. We can take the battery out of the picture, and now we can connect this system, this capacitor, to something else, some sort of electrical device. And now, the electrons that were held against their will over here have an escape route here. They can't jump the gap between the plates because there's air there, but now these electrons can leave this way, through the wire, running this electrical device, and it will discharge itself. In other words, the capacitor will sort of act like the battery was doing, but only for a short amount of time, because it's going to, as these electrons leave through here, it's going to return to its original conditions, it's going to lose the voltage, and so it's sort of like a short-term use battery. We define this capacitor by what is called its capacitance. I know that makes sense, right? We'll define a capital C as the symbol for capacitance, again, something that makes sense. And we say the capacitance of a device is its ability or its capacity to store energy in an electric field. When those oppositely charged parallel plates had that potential difference across them, it's only because the charges were separated in a position where they didn't want to be, and that creates an electric field and stores energy in that electric field. And we'll define the capacitance of that capacitor as this ratio of charge per potential difference, or now what's called charge per voltage. Let's talk about our usual ideas here. First of all, it's a scalar because, hey, charge is a scalar, potential difference or voltage is a scalar as well. What about the units? Well, the top is charge measured in coulombs, sure. The bottom is voltage measured in volts. That's why it's called voltage. And so the units are coulombs per volt. We do happen to rename the coulomb per volt. I'm not sure if anyone's ever heard of it before, but it's named after Mr. Michael Faraday. So it's a capital F in his honor. And the unit is the farad. Now immediately you might say to yourself, wait a second, I thought you just said his name was Faraday. That's true, his name is Faraday, and yet the unit is called the farad. So I don't know what happened here. There's got to be some story, right? Because when the unit is named after a person, the name of the unit is the person's name, and yet someone decided that we're not going to name it the Faraday, we're going to name it the farad, leaving off the last 2 letters of his name. Who did he annoy? I don't know, but he annoyed someone or other, and so they said, oh, we're going to get a unit, but ha-ha, we're going to take 2 letters off your name. I don't know. Anyway, so the farad, 1 farad, is equal to 1 coulomb per volt, and that's the unit of capacitance. In the equation, the Q is the amount of charge on one of the plates. Remember, one of the plates got a positive charge, the other plate got a negative charge, so it's just the amount of charge on one plate or the other. And this being the first time we officially used an equation, we'll define here delta V as the voltage, the potential difference between the plates. And we give a new name to the oppositely charged parallel plates. They're now called a capacitor. And we'll define a capacitor as the object with capacitance. Right? I think that makes sense. So just make sure we use our vocabulary correctly. The capacitor is the object. That's the oppositely charged parallel plates. And what do they have? They have this capacitance, this ability to store energy in an electric field. So going back to the picture again, the capacitor, the plates here, have this potential difference. All these electrons held where they don't want to be. But now, since they can't jump the gap through the air, they have this escape route. One by one, these electrons can leave through this conducting wire, go through some electrical device that uses electricity, running it, and then the electrons end up back on the positive plate where they want to be. But because Now this plate's becoming back to neutral, and this plate's going to eventually come back to neutral. They lose their voltage, and so while this capacitor is sort of acting like a source of voltage, acting as a battery, well, it's going to run out of the energy to do so once everything returns back to its uncharged state. So we also say a capacitor is sort of like a short-term use battery. It does the same job as a battery, because once you charge it up with the battery, it retains that same voltage, but then when you connect it to some other electrical device, as it discharges itself, it loses that voltage, and so it only works for a short amount of time. And then when we draw the capacitor in diagrams, we just boil it down to its basics, just the parallel plate. So this here is the symbol for the capacitor. So it's two lines parallel to each other of equal length, whereas the symbol for the battery had two lines of unequal length. And of course, these are just wires coming off of it.